You know, laser welding is just one of those mind-blowing technologies, right? Using a focused beam of light to build everything from cars to spacecraft. But it turns out this super high-tech process has a tiny, kind of messy, and surprisingly costly flaw. So let's dive in and see what's really going on.
Okay, just take a look at this. I mean, on one hand, it's totally incredible. That beautiful pattern is a perfect bond between aluminum and steel made with nothing but light. But look a little closer. See all those little specks around the edge? All that messy stuff? That's the flaw we're talking about. And yeah, it might look tiny, but trust me, in the world of high-tech manufacturing, something like this, it's a huge deal. All right, so to really get why this is such a big problem, we've got to know what we're up against. What exactly is this stuff? Yep, the villain of our story has a name. It's called spatter. And basically, it's what happens when the welding process gets a little too violent. Tiny droplets of molten metal get launched right out of the weld pool, and they land and harden where they're absolutely not supposed to be. The best way to think about it, it's like a teeny tiny volcano erupting all over your workpiece. Okay, but why should we care about a few stray droplets of metal? I mean, really? Well, for starters, that spatter is material that was supposed to be in the weld. So right away, you're looking at potentially weaker joints. It wastes expensive material and it leaves this rough, ugly finish. But here's the real kicker, and this is important. Think about super sensitive electronics, like the batteries in your phone or in an electric car. These little metal bits can cause short circuits. That makes the final product not just unreliable, but potentially dangerous. Now you see why it's a big deal.
So if you want to tame this spatter beast, you first have to understand it. So researchers set up this great experiment to get to the bottom of what causes it. They decided to focus on two main suspects, how powerful the laser is and how fast it's moving. And here's their lab setup. So over on the left, that's the whole system. You've got a high-power laser firing these super fast pulses. It's aimed at two thin sheets of metal. We're talking aluminum right on top of steel. And on the right, that's the super precise path they programmed the laser to take. I mean, every single detail here was meticulously planned out to get good, solid, measurable data.
But this brings up a pretty big challenge, doesn't it? You've got literally thousands of these microscopic droplets splattered all over the place. How in the world are you supposed to measure that accurately enough to get data you can actually trust?
They came up with this really smart four-step process using computers. So first, they get these super high-powered microscope images of the whole area. Then, they pop those images into some special software. The software's job is basically to go in and digitally find every single tiny spatter particle and separate it from the clean background. And the last step, it just adds up the total area all those little particles cover. Simple, but brilliant. And check this out. This shows you exactly how it works. On the left, that's the raw image straight from the microscope. Kind of messy. But on the right, that's what the computer spits out. See that? Every single one of those white dots is a spatter particle that the software has found and measured. It's how you turn a messy, looks bad problem into hard numbers you can actually work with. So cool.
Okay, so now we know how they measured the problem. But let's get into the real science. What's actually happening on a tiny, tiny scale that's creating all this spatter to begin with?
So, what's the hidden force here? I mean, something has to be powerful enough to literally throw droplets of liquid metal into the air, right? Well, the culprit has a name. It's called recoil pressure. Here's the deal. The laser is so incredibly hot, it doesn't just melt the metal. It instantly turns some of it into vapor. This creates a tiny little pocket, or a keyhole. And inside that keyhole, the pressure from that metal vapor just skyrockets, creating this powerful jet. And that jet pushes back hard against the molten metal around it. If it gets strong enough, boom, it acts just like a geyser, blasting those little droplets right out of the pool. Okay, so that's the theory. This high-pressure jet of vapor is our bad guy. But does the data from the experiment actually back that up? Let's take a look at the evidence. And wow, the data was crystal clear. Just look at this graph. The bottom line is laser power, and the line going up is the amount of spatter. And you can see it plain as day. The more you crank up the laser's power, the more spatter you get. It's not a small increase either. It just shoots right up. More power means more heat, which means more vapor pressure, which, you guessed it, means a whole lot more spatter. So really, it all boils down to two key things that are kind of pulling in opposite directions. You crank up the power, you get more heat, more pressure, and boom, more spatter. But if you crank up the speed, how fast the laser is moving, The metal just doesn't have as much time to heat up and vaporize. And the result? Less spatter. So it's this delicate dance between power and speed. But get this, they found something even cooler. The spatter wasn't just happening randomly all over the place. Nope, it actually had a direction. This chart is awesome. It shows how much spatter you get at the start of the weld compared to the end. And look, the yellow bars, the starting points, always have way more spatter than the blue bars at the end. So, what's going on there? This was the smoking gun. It confirmed that recoil pressure theory perfectly. Remember how that jet of vapor blasts things backwards? Well, as the laser moves forward, it's flinging spatter back in the direction it just came from. So of course, the starting points get coated. This was the proof they needed. It absolutely nailed down how the spatter is formed.
Okay, so now they know what causes spatter, they know which knobs to turn, power and speed to control it. So that brings us to the final and, let's be honest, the most important part. How do you use all this knowledge to actually stop it from happening and get that perfect weld?
See, all that painstaking measurement wasn't just an academic exercise. They took all that data, every single test with every combination of power and speed, and fed it into a computer to build a really powerful statistical model.
And this model is basically a spatter prediction machine. You can just tell it, hey, what if I use this much power and this much speed? And it will tell you, with incredible accuracy, exactly how much spatter you're going to get. It's like having a crystal ball for welding. It's amazing.
And that is the real payoff here. For manufacturers, this is a game changer. No more expensive, time-consuming trial and error. They can just use the model to find the sweet spot, that perfect recipe of power and speed that gives them a super strong, super clean weld with almost no spatter at all.
All right, I know, we have gone deep into the world of tiny molten metal droplets. But let's pull back for a second. In the grand scheme of things, why does spending so much time and effort on such a tiny problem matter so much?
It's because fixing the tiny flaws is how you get the big breakthroughs. It's that simple. Getting rid of spatter makes manufacturing way more efficient, with less waste. It makes the batteries in our phones, our cars, safer and more reliable. But really, it's just a fantastic example of how science and progress actually work. You have to patiently, meticulously, obsessively understand the small stuff, because that's what paves the way for the next giant leap. And that just makes you wonder, doesn't it? What other tiny, invisible flaws are out there right now? These little bits of spatter in other fields, just waiting for someone to solve them, and in doing so, unlocking the next wave of technology that we can't even begin to imagine today?